as promised, I am now going to demonstrate the hash puzzle. A hash puzzle has two transactions. One is when you build the locking script, and that is the puzzle. And the other is when you build the transaction, which is the claim. So we'll do three things. First, I'm going to, walk you through it on paper here on my iPad. Then I'm going to show you in my terminal where I have the two programs that run both builds. And then we'll go out on WhatsOnChain. All right, to start, the locking script for this hash puzzle, and there's lots of different ways you could do a hash puzzle. This is a really simple way. And taking a step back, basically, let's pretend there's a website out there and it says, what was the pseudonym for the creator of Bitcoin? So that's the question. And we're going to lock up the puzzle. Right now, I'll show you how that works. All right, so the first opcode is simply op SHA 256. All right, the second one is a data element, and that data element is a 32-byte hash. And what is this hash a fingerprint of? It is the answer. It's embedded in a hash in the puzzle. Why is it 32 bytes? Because SHA-256 is a hashing algorithm that deterministically always gives you 32 bytes. You could put in 2 letters, you could put in, 50 numbers and characters, whatever it is, it's always going to be 32 bytes. All right, and then the third element of this locking script is op equal. Okay, that's it. That's the whole locking script. Now to unlock it in the claim transaction, it's even simpler because all it is, all right, so let me write up here, this is the lock script. So the unlock script is, it's data. And what is that data? It is Satoshi Nakamoto. Okay, that's the whole unlock script. I mean, there's a tiny little push data opcode on there, but you don't have to worry about that. And that's the same with up here in the lock script, that there would be a tiny little push data opcode on there. But this is, for all intents and purposes, this is the lock and the unlock script for this hash puzzle. So remember how we did it last time where I showed you the recipe for unlocking and then the stack? That's how we're going to do it here. So we are going to put recipe on the left and stack on the right. So what is the recipe? So the recipe is the part where the miners are verifying to make sure that you have a right to spend, unlock a locked script. Okay, so the way that it works is they put together first the unlock and then the lock. So we have our whole recipe here. And we are about to do what the miners do when they verify to make sure that you have a right to spend that lock. And again, I want to remind you what's really unique here is that when that first transaction, that lock was written, it wasn't noted that it was to go to any particular public key. Okay, it could be anybody on the planet. So we didn't indicate a key. We only indicated a script. All right, so the first thing that we do is we pop the first thing on the recipe over onto the stack, and that's data, because it's only data that goes on the stack. All right, so let's check this part off because we did that part of the recipe, and now what's next? It's an opcode. So now we are going to do an operation on whatever on the stack there, and what we have are the words Satoshi Nakamoto, which is someone's guess at what the answer is to the puzzle. So we are going to do a SHA-256 hash of that, and what do we get is a 32-byte hash. Okay, and this guy goes away. So what do we have left on the stack is this hash that we just created. Super. All right, that part of the recipe is done. So what is next is this 32-byte hash that is part of the locking script goes over. So now what do we have? We have two 32-byte hashes of data on the stack. So we're going to check this off because we did that part. We now have one opcode left, and that is op equal. So op equal is looking at the top two things on the stack, and it says, are they equal? And we know that that's true. Satoshi Nakamoto is the pseudonym of the creator of Bitcoin. If anything had been invalid, then the miners would have tossed it out, and we would not have had a empty stack equals true. So we have a valid transaction, which means that whoever wrote that transaction to claim the hash puzzle amount, which I forgot to tell you is 1,000 sats. Now let's go take a look at me running both of these mini programs in the terminal. All right, so here we are, and I am about to run a program that I've already written that is broadcasting a transaction, and it is that lock, that puzzle. And so I'm going to hit enter, and there it went. All right, we'll go look at that in a moment, but first I want to claim it. So this wrote the puzzle, and you can see it's on WhatsOnChain. And this is just in the program. So this is output that says what happened. So we wrote 1,000 sats, sent 71,450 sats back to me, the writer of the puzzle. And we locked it with that locking script. So here's op SHA-256, and here's op equal. And here is that 32-byte hash. So now I'm going to claim it. And so let me pull up that claim transaction. Yeah, this is right. I have to edit it a little bit, but notice here that the first thing after claim, which is the little mini program, is, in fact, it even tells us what we need to do. We have to put the transaction ID of the hash puzzle. Okay, so we're going to take that transaction ID, the new one, because this is an old one that I ran earlier. This is the hash puzzle transaction, and the answer is Satoshi Nakamoto. Now, what is this third element, do you think? The third element is what we put in the output when we write this new claim transaction, because we have to tell it where to send the money that we just got, the 1,000 sats we're about to get. Unless somebody else beat us to the mempool. Well, actually, unless somebody else beat us, and then I'll tell you the mempool thing in a second. So that address is my address, but it could have been anyone's, right? I could have sent it to my friend with their address. But anyway, so we're about to broadcast this. Let's see what happens. And there it is. The claim on mainnet broadcast. My answer hash is to this, and the puzzle wants this. They're equal. The answer satisfies the lock. So the payout is 989 sats to this address. Now we are going to go look at what's on chain, and I can show you both sides of the transaction. So here we are, and you can see it's unconfirmed. And this is the second transaction, okay? We'll show you the first one in a second. So on the left here, these are the inputs. So this is a script hash, so we're not looking at an address here. And it shows it that it's spending from this transaction, so 709EB, and the 0 index for it. So here you see the locking script, and then you see the unlocking script. So here's the fun part. See Satoshi Nakamoto, it's right in there. So when you do a hash puzzle this way, the answer is revealed as soon as you write the claim transaction. So just showing you that again, Satoshi Nakamoto. And then I'll show you the locking script just so you see it in here too. Opshaw 256. There is the 32-byte hash, and here is op equal. Now go to the output side, and this is really simple. It just spends to my address a classic P2PKH transaction. So now let me go to the originating transaction so you just can see that, and that's this one here. And the lock over here, there's two outputs. One is change to my address, and one is that locking script. So let's look at it. It's going to look familiar. It's that Opshaw 256 32-byte hash op equal. So there you have it. It's the whole thing. I am going to put the code up on GitHub, and I'll link it in the description so you can play with it. I hope this was fun, and perhaps you can see your mind is racing on all the possibilities that you could use this unique script for.
Got a curve in the game.